In this tutorial, I'm going to be outlining how to use MENOTR to fit an experimental data set, shown through here, with a reaction scheme, or to a reaction scheme. So the reaction scheme we're fitting our data to is this, where we have two different species, A and B, which is reversible with the rate constants K1 and K2. And so the goal here is to figure out the parameters K1 and K2 that best describe this experimental data set shown below. Now the data set we have is our independent variable is time. Here we're only monitoring the second species, the species B, and now we're just assigning the standard deviation values of 1 for all of the measurements of the fraction B. So now the first thing we need to do in this process is to write out a elementary differential equation describing each individual species present. So we have A and B. So here those are written here, where we have dA dt is equal to minus K1 times A plus K2 times the concentration of B. And then we have dB dt, which is equal to K1 times A minus K2 times B. So now that we have that in hand, we can now move on into MENOTR. So now here's our working directory. We're going to go into our MENOTR master scripts. We can copy over our chemical reaction scheme. So we're going to go to the chemical reaction scheme and copy over that folder. Copy and paste that into our working directory. And we're going to copy this into our MATLAB. Okay, so now here's that Excel file with our experimental data. Now the first step within MENOTR to go about this process is to open up our scheme. So now our scheme file is just going to be loading our reaction scheme into the MENOTR code. So how we do that is first, I would like to point out that the sections that need to be modified are section 1, section 2. So the first thing we do is identify our species. So A is equal to species 1 and B is equal to species 2. So if you're in your model, I would encourage you to go ahead and assign individual characters for each of the species present. So now in the second portion, or section 2, we're just going to be loading in the set of ordinary differential equations, where we had the first is minus A times K1 plus B times K2, which is shown here. And then the second one is A times K1 minus B times K2, which is shown here. Just follow the syntax as shown here. And this is all that needs to be done for the scheme. So now we can save that and close. Next, we're going to open up the model simulator. And we're going to need to modify sections 2 and 4. So if we go down to 2, here we're just defining the parameters. So K1 is params 1, K2 is params 2. We're going to have an amplitude term. So the amplitude describes how much of the reaction goes to completion. It also can account for if you're measuring fluorescence or something of that sort. So here we have an amplitude term times params 3. Which is the params 3, excuse me, not times params 3. And now we have our model parameters, which are both K1 and K2. So we just load in those elementary, those rate constants, K1 and K2, into here. And if you have additional ones, they'd be loaded here. We have our initial concentrations for each species. So you have the two species A and B. I want to have the initial concentration as 100 micromolar for A and 0 B at the start of the reaction. And now we're going to normalize to 100 micromolar also. So by normalizing in this way, we're going to start out at 100% at A or 1, and then we'll slowly move to B. Now, this is all that's in section 2. Now moving on to section 4. Section 4 is a little bit complicated, so bear with me. So if we think about from the scheme here, if we simulate a time course from this scheme, we get a set of time courses for each individual species in the model. So we get a time course for both A and B, but we're only monitoring the B species. So we need to match what we're simulating to what we're seeing experimentally. So how we achieve this is when we simulate from the scheme, shown through here, we generate this matrix called sim species time courses. So this is a matrix which contains all the time courses within for each individual species. And now within this matrix, there's each column corresponds to a different species. So the first column corresponds to the A species. The second column corresponds to the B species. If you have a C species, the C would be the third. So each column is a different species, and then each row going down corresponds to your different time points. So you're monitoring each species as a function of time. And those time courses are all in this matrix called sim species time courses. So now we need to define which of these are our actual experimental product that we observe. So that's the product simulated time course. So we're only seeing the B species, right? So thus we're going to define the product simulated time course as the second of the sim species time courses. So this is saying all the columns, or excuse me, all the rows of the second column. So this is calling the second column within the sim species time courses. So remember what I said a moment ago, that this matrix called sim species time courses is one large matrix that composes all the individual species. And now we're just going to call the second one. And the reason we're calling the second column, and the reason we're calling that second column specifically is because we're looking for the B species. So if you're looking for A, it would be 1, B is 2. So we're calling this second species, which is the B, and we're saying that that's the product simulated time course, or what we're observing here. So now, and that's all that needs to be modified. So we have both 3, 2, and 4 have been modified. So now we save that. And now we go to step 1. And step 1 is like the other step 1s where we just run the code. And then we put in our experimental data in the form of where the independent variable comes first, the dependent variable comes second, and then the standard deviation is third. So we can copy these, copy and paste over. And now we can close this and close this. So now the insert data has been loaded into the code, or loaded into the MATLAB workspace. Now, if we open up step 2, next we're going to be defining the parameters that are in our model. So we have K1, and then we have upper bound, lower bounds. Let me back up. So we have initial guesses for each of the kinetic parameters, as well as the amplitude, as well as upper and lower bounds. So we're going to define the initial guess of 10, an upper bound of 100, lower bound of 0.001 for K1. Likewise, the same for K2. And then a amplitude of 1, the upper bound value of 1, and a lower bound of 0.01. So now we're putting in those initial guesses, upper and lower bounds. And now we're just going to organize those parameters like so, where our param vals composes each of the individual parameters, K1, K2, and K amplitude. Params upper bound, or params underscore up UB, is just each of the upper bound terms. The lower bound terms are loaded in, and then we type out all the parameters to be cleared, to clear up the workspace. And this is all that's done for section 1. So now we need to modify section 2 also. So section 2, once again, we're going to be editing the cycles, or the iteration control vectors. So this corresponds to the first cycle. We're going to perform 5 generations of the genetic algorithm. Without non-linear squares on, we're going to allow the parameters K1, K2, and the amplitude to all float. So that's dictated by the 1 on the right-hand side. Underscore C indicates that we're talking about the cycles matrix. And then parentheses 1 indicates that we're dealing with the first cycle. And now we're not going to perform non-linear squares in the first cycle. Now in the second cycle, we're once again going to perform the genetic algorithm, but now we're going to do 5 generations of the genetic algorithm with non-linear squares being present. So now we're in the second cycle, as shown. The parentheses 2 indicates the second cycle. We're once again going to have the parameters K1, K2, and the amplitude all floating parameters. So those are all 1. And now we're going to have non-linear squares. So we're going to have 1 there. So now for the SciMat, which is, so now we're just loading in these parameters. So we're going to have K1 underscore C semicolon, K2 underscore C semicolon, amp underscore C semicolon, and non-linear squares. And then, so you just type those all in from here. And then we have clear for each of those variables. And now So we've modified both 1 and 2. So now those are done. And now once it's been modified to match your corresponding model that you're working with, as shown here, then we just run this code. So now it's by running this script, we have loaded in a bunch of different parameters into the workspace, and now we're ready to execute the fit. So now we just open step 3, and we can run the fit. So as you can see, we're now fitting our experimental data. And as you can see, we're going through each of the 5 generations before going over into the next cycle, and then the next optimization routine. And we're getting better and better fits, as shown by the best fit line describing the experimental data and the chi-square going down. Okay, so now after each of the optimization routines perform their 2 cycles each, the resultant chi-squares are all pooled together. So as you can see, they're all shown through here, and they were all compared to one another, and there wasn't a statistical difference between the two. They're all identical, as you can see. So the code stops and the fit is now complete. So now we have a figure as shown here, final plot TIFF. So if we open outside of MATLAB, as you can see through here, we have pretty good fits of our experimental data, and we have a plot of the fit residuals. Our fit parameters, so those values of K1 and K2, our K1 was 4.2 or 4.3 about, and our K2 is 0.8, and our amplitude was about 1. We have fit chi-square, we have our experimental data, we have the plots of the residuals, as well as the simulated data, which corresponds to that best fit line shown here. So here we've been able to determine that the parameters that best describe the experimental data are K1 is approximately 4.3 and K2 is approximately 0.8, which describes this experimental data. And here I've shown you how to use MENOTR in fitting experimental data using a reaction scheme and how to optimize the parameters within that reaction scheme.